Hi, my name is Steve. I'm a professor at Williams College. Welcome to Teachers as Scholars, and this is going to be the first of the Algebra is Fun series. And so what I want to do right now is I want to shift to, let's start off with a game, the I Love Rectangles game. So let me just make sure it's recording. It is recording, excellent. So this is a game that I have played with elementary school kids starting as low as kindergarten. So this is really supposed to be something that is accessible. Just minimize. Okay. Okay. Okay, so our goal is to explore tiling. So what is a tiling? So we have a collection of objects and we want to cover space. So for example, imagine we have a really large carpet, a 10 by 10 grid, say, and we want to use shapes to cover it. So any thoughts as to what would be a good shape to use to cover this grid?
Squares.
Square, yeah.
Squares. So
Rectangle.
this is screaming at you, please use a square. If we have a bunch of 1 by 1 squares, it's not going to be hard to cover. We start in the corner and just keep moving, not a big deal.
Right.
This is not exciting. Building on the success, one thing you could ask students is, well, what else could you use to cover? So a square is a regular polygon, all equal sides, all equal angles. You could try an equilateral triangle, and you'll see very quickly that that works. And that would also give you a regular hexagon. And then you can ask, what about other shapes? Would those work? This is a nice thing for the students to explore. You can cut these out. You can make it a nice physical activity. Now, let's change it a little bit. So what we were doing before, we had one shape, and we had as many copies of it as we needed. Now what we're going to do is we're going to have still one shape, a square, but we're not going to have as many copies as we need, potentially. We're only going to have one 1 by 1, one 2 by 2, one 3 by 3, one 4 by 4, one 5 by 5, and so on and so on and so on. So every shape is a square, but each size square we have once and only once. And we want to cover. And to make it even more interesting, we can only put them down one at a time, and at every moment in time, our shape must be a rectangle. So is this possible? So when I go to the schools, I say, I can do one square on the table, keeping it a rectangle. If you can do better than me, if you can do 2 squares, I'll give you $20. And just to protect myself, I take out 20 Canadian. I am not that far from the Canadian border, so I keep some Canadian money on me. Is it possible to put down 2 squares and have a rectangle? What do you think?
Sure.
I'm sorry?
I think so.
So which square would you put down first?
Um,
Remember, you only have one of each. So what would you put down?
I'm not sure I'm understanding the rule here.
Okay, so you see all the different shapes we have.
Yes.
You choose a shape and you put it down. And because a square is a rectangle, the shape you have on the board is a rectangle. You no longer have that shape. So you put down the 3 by 3 or the 4 by 4, we would no longer have that available. Then you have to choose another square and put it down. You can't put it on top of the previous one. And you must still have a rectangle. So for instance, imagine we place the 4 by 4 square first. So what do we have left? We have a 1 by 1, a 2 by 2, a 3 by 3, a 4 by 4. I'm sorry, not a 4 by 4, a 5 by 5.
Yeah.
Is there anything that we can put next to the 4 by 4 and still have a rectangle?
I don't see how, but there must be a way.
Why? I'm not a nice person. When I go to the elementary school, by the time the kids get to 5th grade, they realize all of my games are rigged. In the younger grades, they still think they can beat me. Say we try to put down a 3 by 3. Well, the 3 by 3, it's not going to be the right size. It's not going to fit.
Right.
So you can do this with every shape. If you have a 4 by 4, the only thing that you could put down to keep it a rectangle has to have a side of length 4, and none of them are left.
Right.
Right.
A boring game. After one move, it's done. So we need to make it a little bit more interesting. So let's take the squares I gave you, the 1 by 1, the 2 by 2, the 3 by 3, and so on. I have to give you something. If I just leave it like this, you can only put down one piece. So I'm going to give you one more square. So I'm going to repeat one of these. What's the smallest square I could repeat?
1 by 1.
The 1 by 1. So I'm going to give you the least amount of things I can do. So can you do it now?
Yes. Oh,
What would you put down first?
I'd put down the 2 by 2.
yeah.
The 2 by 2 square? You can only put down one square at a time.
Oh,
So what square should you put down first?
the 1 by 1.
Yeah, you put down one of the 1 by 1s.
Okay.
And now we're left with a 1 by 1, a 2 by 2, a 3 by 3, a 4 by 4, 5 by 5, and so on. Now
Yeah.
you put down
The other 1 by 1.
the other 1 by 1. And in a method of wonderful animation, you see how the square changes color as it collides? It's wonderful.
Very nice.
What do we do now?
2 by 2.
The 2 by 2. And so we put down the 2 by 2. This is all just done in crude graphics in Microsoft Paint. Again, the perfect is the enemy of the good. This is just trying to get stuff up. So what would we put on next?
Uh-oh.
Yeah.
Well,
Well, we have a 2 by 3 rectangle. So what could we put down next?
That one.
3 by 3.
The 3 by 3. Now there's actually two choices. I could put the 3 by 3 on the left or on the right. I'm going to choose to put it on the left. Now I have a 3 by 5 rectangle. What should I put down?
5 by 5.
The 5 by 5.
Up.
The 4 by 4 does not fit, and we're going to put the 5 by 5 and we're going to put it up. We could have put it down, but I'm going to choose to put it up. So now, what should we put on next?
Oh, we have 2 of everything, right?
No, we only have 2 of the 1 by 1.
Oh, okay. You just said,
Everything else we only have 1 of.
so there's only a 4 by 4 left.
No, but we also have the 6 by 6, the 7 by 7, the 8
Oh.
by 9.
8
Oh.
by 8.
Unfortunately, due to budget constraints, I don't
No.
have the infinite screen today, so I can't show all of them. So we would put down the 8 by 8.
Yeah.
And so we could keep going and going and going. What would be next? We now have an 8 by 13.
13 by 13.
And what we see is we don't use a lot of the squares. We never use the 4 by 4. We never use the 6 by 6 or the 7 by 7.
Right.
So let's write down the squares we used in order. We used the 1 by 1, the 1 by 1, the 2 by 2, and so on and so on. Well, since they're squares, I can just write down their side length. 1, 1, 2, 3, 5, 8. Do you notice a pattern?
Mm.
Have you seen?
Yes, you're adding.
You add the preceding and the next, you get the total of the third.
So how do I get 8?
So 1 and 1 are 2, 1 and 2 are 3, 2 and 3 are 5.
Wait, so exactly, you add the previous 2 to get the next.
Right.
And so this is the Fibonacci sequence.
Oh.
So this is a way for students to discover the Fibonacci numbers.
Hmm.
That's pretty awesome.
And so you can do this just by playing a game of covering the plane. And there's so many other ways you can go. You can talk about other kinds of tilings you can do. And so we notice the pattern. There's a wonderful video. Do you want to see a 3-minute video, or do you want me to just the link?
No, go ahead.
All right.
Go for the
What I'm going to do
video.
is I'm going to stop the share. And let me just move. Oh, looks like we have somebody else who's joined us. Hello, Nathan.
I think he was muted.
Hello, how are you?
Yes.
Oh,
How
I
you
know.
doing?
I was then.
running a little bit late. I was Zooming with my 5th grade math class.
No problem. Okay, we're recording right now, so I will have you share that stuff later.
Super.
Now I am playing a short movie clip. It has mandatory cheesy music. So this is a nice clip on the Fibonacci numbers. So each one is the sum of the previous two. It starts 0, 1, 1, 2, 3, 5. And what they're going to show you is this is the tiling we were talking about. And you can see there's the 2 1x1s. There's the 2 by 2. There's the 3 by 3, the 5 by 5. And now you can see why I was putting the squares in the order I was, is I wanted them to spiral up and get the Fibonacci spiral. That was what was motivating my choices.
Yep.
And then what it starts to do, it shows you a lot of different places where these occur in nature.
I had a bad elementary math teacher, I think.
So you can do, I mean, again, they didn't have these videos when you or I were children, but there's so much good math you can do at an early age. And so right now, we're seeing a shell. The next one we're going to get into has some nice biology applications. So the golden mean is the ratio of adjacent Fibonacci numbers as you go further and further down in the sequence. It's about 1.6. It's actually 1 plus √5/2. And they're showing right now how you can actually get an angle from the Fibonacci numbers. So I'm not going to really go into too much detail, but it's basically dividing up the circle so that the ratio of the two parts is like the ratio of the Fibonacci numbers. And what we do now is we have a Fibonacci gun and we shoot out a bullet every Fibonacci angle, 137.5 approximately. And as you shoot them out, they continue to move further and further away from the center. And in a moment, you will start to see what this is meant to be. So just wonderful applications of where you see this stuff in the world. Another place where you see this is how leaves grow, because you don't want to have one leaf on top of another that's going to affect the ability to capture sunlight. And so you can talk to the kids in science, what is a leaf doing for a tree? It's trying to capture sunlight. So when you have new leaves, the leaves on the bottom are typically larger than the leaves on the top. How do you design where the leaves are so that they don't overlap, so they maximize the amount of sun that they can get? And then they're just trying to show you other places where the Fibonacci numbers would occur. This one wasn't quite as interesting. I'll fast forward a little bit. You'll see it in wings. So, okay, so I'm going to stop there because that was the best part of the video. I will go back to the slides. Okay, so we just saw how by playing a tiling game, we can get our students, and I've done this with kindergarten kids, to the Fibonacci numbers. And so we have the pattern 1, 1, 2, 3, 5, 8. Now this can become an addition challenge. See to the kids, how high can you add? How far can you go? Now, here is an advanced item. This is not something I would do in kindergarten, but so here's the Fibonacci spiral. And this allows you to do a wonderful thing called proof by picture. And so we have this rectangle, and this rectangle is 21 by 34. So if I wanted to find its area, I would just multiply 21 by 34. But there's another way to calculate the area. This rectangle is completely covered by non-overlapping squares. So if I just sum the lengths, the areas of all the squares, I would get the area of the rectangle. So I get 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared plus 8 squared plus 13 squared plus 21 squared is equal to 21 by 30 times 34. So we have just given a geometric proof that the sum of the squares of the first n Fibonacci numbers is the nth Fibonacci number times the n plus first Fibonacci number. So this is the power of a geometric perspective, that you can actually give an interpretation to some algebraic quantities. You can also talk a little bit about units. If you think about the Fibonacci numbers in meters, this is going to be sums of squares. This is going to be meters squared. That's an area. That makes sense that it would be the product of two different Fibonacci numbers. If you know proofs by induction, you could prove this by induction as well. it's a classic induction problem. I prefer the geometric picture because it tells a really nice story. There's a lot more stuff you can do with Fibonacci numbers. The whole purpose of this module was to just try to show you, a little bit of a game that you could play, a quick introduction for your students where they have a physical activity. Does
Stephen, can I
comment?
ask
Yes,
you a question?
absolutely.
So that's fascinating. I didn't know anything about that. How would you explain just briefly to say a young student or to say an English teacher, for example,
Right.
why Fibonacci numbers are important? Not that you're going to explain every single thing about them, but once
Right.
they do the tile thing, then you say Fibonacci numbers are important because.
So I would say there's a couple of ways. One is they occur in biology, and you can talk about how plant and nature is structured. Why does nature choose these things? That is sometimes above my pay grade, but you can talk about the structures that are observed in nature, and you can start to ask, why might we be seeing stuff like this? And what we're seeing here is that there's a lot of power with the Fibonacci numbers. They are also an example of a difference equation. So Fn plus 1 is Fn plus Fn minus 1. So what it's telling you is where you are at state n plus 1 is the sum of where you are at state n and state n minus 1. Difference equations are discrete versions of differential equations, which describe so many phenomena in the world. Your Newton's second law, your F equals ma, this is a differential equation. Difference equations have a discrete advance in time. And so the way we solve Fibonacci equations is actually related to a lot of other things. One of the things that I often do in seminars like this is I analyze the game of roulette. So if you've ever played roulette, you know that the casino is not in business to make you happy. Well, maybe to make you happy, but not to make you money. The casino is in business to make themselves money. The following is considered a very simple strategy to win at roulette. You bet on red, and you bet $1. If red comes up, you win $1. If not, you're down $1. So you bet $2. If red comes up, you've won 2. You lost 1 before, so you're now net $1. If not, you're down 3. So now you bet $4. If you win, you net $1. If not, you're down 7. And you keep doubling your bet, and eventually you win $1. And so the strategy is called double plus 1. And at first it sounds wonderful. The question is, why am I giving this lecture not in Vegas? Well, okay, I'm not allowed to fly nowadays, but in earlier days, why wasn't I in Vegas doing this? Well, there are 2 problems. The first problem is you might get to the point where you have to put down $10 billion. So, I'm not an economist, but I have a lot of friends who are, so I will borrow an idea from their discipline. It's called the unreasonable assumption. So I will assume the existence of an eccentric rich aunt and uncle who love me and will stake me in any bet I need to do. They won't give me $1, but if I need $10 billion to make a bet, they will provide it to me. So that's not the problem. The problem is how Vegas sets up the betting. You have a table minimum and a table maximum. And if you get too many losses in a row, you can no longer place that double bet. And Vegas knows this math extremely well as to how to calculate it.
Wait a minute, Steve, what do you mean? If you lose?
So every time I lose, I have to double my bet. So say
Right.
the minimum is $1 and the table maximum is $40.
Right.
If I lose $32, the next bet I have to do is 64, but I'm not allowed to bet 64. I can only bet 32. So what happens is when you win small. When you lose big.
You lose big.
And it turns out that the analysis of this, and if you send me an email, I'll send to you. I've got a video on this. It's about 8 minutes. It's an analysis of a generalization of the Fibonacci numbers. It's a very similar difference equation that proves why you have no chance at this game. And so
The Fibonacci numbers aren't just structural, they're also other sorts of principles.
right, and so the Fibonacci numbers are an example of a wider class of phenomena. You know, we often see them in architecture, we often see them in proportions of pictures and whatnot, but that's almost by human choice. But the more general principle, I have a sequence where my later values are determined by my earlier values. In some sense, this is almost all of deterministic science. How do you figure out your next state given where you are? And for some things, you need to know more than just where you are, you need to know where you've been. So how much of previous history do you need to know? I just threw up one more slide. This is something that my daughter and I made a few years ago with a little help from my son. We used the Fibonacci spiral.
What are those things? Are they, they're not.
These are fuse beads. You put them down, and then you put a piece of wax paper over it, and you iron it, and it fuses. Then we actually did the 55 by 55 square, a year or so later, and boy, did that take a long time, because 55 squared is over 2,500 fuse beads.
That's great.
But so I hope this gives you some sense of why the Fibonacci's. It's a great question to ask. And again, to me, a lot of it is to teach someone to fish versus giving them a fish. When you learn how to solve something like the Fibonacci's, you can then apply that knowledge to a whole wider class of phenomena.
Cool. Yeah.
And any other comments on this one? Okay, I'm going to end this, upload the recording, and then just open up the meeting again in about a minute.
Okay.
Use the same link to come back on.
All right.